Alright, so let's take a look at the aluminum foil lab calculations, which so many of us had some difficulty with. We're going to start off with finding the density of our cube. Knowing that the aluminum foil and the cube are both made out of aluminum, we know that the density is going to be the same for both, so that's kind of the key thing to keep in mind here. So I'm taking my measurements from the cube, so you were told to put in the numbers you actually measured. These are all in centimeters. So when I divide the two numbers, or divide this by these three numbers multiplied together, I get my density, 2.87 grams per cubic centimeter. So the reason we found this is because this is our experimental density, and we are using that to apply to finding the dimensions of the aluminum foil itself. So calculation number 2, volume of the aluminum foil sample. So I know the mass of the aluminum foil was way, way, way less than the mass of the cube. So I do know, though, the density is the same, so the density equals m over v, and I am using my 2.87 grams per cubic centimeter. So I'm looking for the volume. So this is where some of us with our algebra need to be very, very careful. And again, if I'm solving for volume, I have to get volume out of the denominator. The mass I have, which is 0.306 for my aluminum foil, is going to go there. So let me just take a look at what this looks like. So D equals M divided by V. So I'm going to multiply both sides by V. That gets V out of the denominator. But now we need to isolate V. So I'm going to divide both sides by D. So that leaves me with volume equals, and then that's mass divided by density. So when you solve for, well, I'm plugging in here, so my volume is going to equal 0.306 grams divided by my density, which is 2.87 grams per cubic centimeter. Okay, notice the grams cancel. This cubic centimeter unit's in the denominator, so that leaves me with a volume in cubic centimeters, and this is a very small number. So it's 0.107 cubic centimeters for my aluminum foil. So it should be less than the volume of the cube as well, because it's very thin. And again, if I plug this back into the density equation, so 0.306 divided by 0.107 should give me back the density 2.87 that I started with. That's how you check your work. And you need to check your work because that's where some of us are going wrong. All right, number 3, the thickness of the aluminum foil. So I know that my aluminum foil is this rectangular piece of foil, and let's see how my art skills are here. So I know that I can measure the length. I know that I measured the width, but the height or the thickness, that was too thin to get with the ruler. So what we now know is the volume of our piece of foil. So if I know my volume of my piece of foil, I know that volume equals length times width times height. So I have the length and the width measured. The height is what I'm going to solve for because I now have my volume to plug into here. So again, rearranging this, I want to divide both sides by length times width, just so I have it. So my height or my thickness is going to be the volume divided by the length times width. Now, the ruler that we used consistently every time has markings at the 100th of a centimeter. It has markings at the 10th of a centimeter, which means we're required to report our measurement to the 100th place. So, that's what I'm looking for in this, is watching your significant figures. 0.107 cubic centimeters. This had 3 significant figures because these numbers all had 3 significant figures. My length, this is for my particular piece of foil, yours is going to be different. This is 8.95 centimeters, and then I had 7.75 centimeters. And again, I have 2 decimal places on all my length measurements. Notice my lengths, using the same ruler for that cube, 2 decimal places, very important. Okay, so then I do this math out. Notice that centimeter and centimeter cancel out with 2 of these centimeters, so my answer is going to end up with centimeters as a unit, and that makes sense because this is a length measurement. So 0.00, and I'm off the paper here. I'll do that over here. Where am I here? 0.0154 centimeters. Again, 3 significant figures, 3, 3. My answer has 3 significant figures. Okay, remember leading zeros don't count. All right, so that's a very, very small measurement. So that's why you would want to change between units. And so to convert from centimeters to, let's see, we were asked for micrometers, micrometers, if you will. Then for B in number 3, I'm going to take my 0.00154 centimeters. And I know that there are 100 centimeters equal to 1 meter, just using the relationships from the table I gave you. And then there are, for every 1 meter, there's 1 times 10 to the 6th micrometers. So you're essentially multiplying by 10,000 when it comes down to it. And so this ends up as 15.4 micrometers. And make sure that you're putting the prefix before the base unit, so you don't just put the micro symbol. And also some of your micros look kind of like capital M's, so this should not look like a capital M. It's a distinctively different shape and symbol. Okay, so there's number 3. So volume of a single aluminum atom. So this threw some people for a loop. Again, we haven't yet talked about the definition of the mole and the molar mass, but we know that for our aluminum foil, that, let me take another sheet of paper here. We know that for our aluminum foil, we had a mass of, where's mine, 0.306 grams. That was the mass of my aluminum foil. Okay, so just like I did before, well, if I want to know how many atoms that is, because again, if I have a volume for my aluminum foil, well, again, just thinking about the picture here, all of these atoms together, my volume total is equal to however many atoms there are, so N will be the number of atoms, times the volume of an individual atom. Right? So if I can figure out, well, I want to find the volume of the atom, I know the total volume because I just figured that out for my foil. So the idea is to calculate, well, how many atoms are there? And I can divide this total volume by this. So if each atom has an equal volume, then dividing the total by the number of atoms gives me the volume of a single atom. So figuring out the number of atoms. I have a mass. I have a relationship between mass and number of atoms, and that is that molar mass that was given you at the top of the page. So similar in setup, if I want to convert from the unit I have to the unit I want, I'm going to do this, 26.98 grams, and that is equivalent to 6.022 times 10 to the 23rd atoms. So the number of atoms in our foil should be a gigantic number, and that's because, well, atoms are very teeny tiny, and so to make up a sample size that is big enough for me to see and measure, it's got to be a whole bunch of them. So 6.83 times 10 to the 21st atoms. So again, if this is my equation that I'm using to figure out the volume of a single atom, well, then I take my total volume, which I found above 0.107 cubic centimeters, and divide by 6.83 times 10 to the 21st, because this is the number of atoms in this particular volume that I found out. Okay, so again, this is atoms. So some people were reporting their number of atoms as their volume, but again, if we're looking at the units, it doesn't make sense. This is the number of atoms, and this is a very, very small number, 1.57 times 10 to the negative 23rd, and so this is cubic centimeters, and that's per atom. Okay, so moving on to number 5, radius of aluminum atom. So again, the formula for volume, for assuming all of our atoms are perfect spheres, we have the volume of a single atom right here, so we'll plug that in here. This equals 4/3 pi r cubed. Well, let me show you the algebra first. So first I'm going to multiply both sides by 4/3. All right, so we should know, I'm sorry, 3/4. That'll get it to cancel. See, there's a 3 and the 4 cancel. Then I'm going to divide both sides by pi. So my equation is going to be r cubed is equal to 3/4, and the pi is in the denominator here. So I'm going to put the pi next to the 4, and then that's times v. Okay, and then we're going to do the cube root, which on your calculator is going to be, you can do r to the 1/3, or sorry, the r cubed raised to the 1/3 whenever you solve for that. Or on the scientific calculators is another way to do that with the cube root button. And so then for my numbers, when I do all that, so thing I need to keep in mind is if this volume I'm plugging in is in cubic centimeters, when I solve for r, I'm going to get a number that's in centimeters for the radius, because it was the radius in centimeter times centimeter times centimeter. And so I actually already did my unit conversions on this, but 1.57 times 10 to the, let's see here, what does this number come out to in centimeters? I did my conversions ahead of time, so that's why my numbers are looking a little bit different here. So 1 times 10 to the 12th cubed times, all right, so 1 times 10 to the negative 30th. Sorry, I did my work differently on my paper here. I don't want to lose you. And the radius I come out with is centimeters, then I have to do the conversions, whatever the radius is in centimeters. And then we have 100 centimeters for every, let's see here, pico is 1 trillion, right? It's 1 trillion picometers equal to that. And so whatever you come out with. So my answer comes out to be in picometers 155 picometers with my numbers. Okay. So then moving on, number 6, how many atoms thick is the aluminum foil? So if my thickness, and my atoms are all stacked on top of each other, and there's some thickness, that's the height that we calculated back in number 3. I know that the radius from geometry, so this is the radius, I know that the diameter is, well, that's 2 times r. So basically, if I can figure out how many of these are stacked up to each other to make up this height, so each of the diameters times the number of atoms equals the height, right? So that's kind of the idea here. So we just figured out a radius. I do need to watch my units here. So if I'm putting this in picometers, so again, my diameter will be, what will that be, 310 picometers times my number of atoms, which is going to equal the height. And my height that I solve for, that is the thickness of the foil, and that was 0.00154. And let me just do a real quick conversion here. Centimeters, if I want to do that in picometers, 100 centimeters times that picometers. So 0.00154 times 1 times 10 to the 12th divided by 100. And in scientific notation, that's 1.54 times 10 to the 7th picometer. So this is my thickness just reported in picometers. So I'm dividing, right, 310. So this is going to give me the number of atoms. I'm expecting this to be a really large number of atoms because, again, this is well, it's something that's big enough to be visible to us. Again, watching my significant figures. So this technically had 3 significant figures. This number has 3 significant figures. This number has 3 significant figures. So the answer I get, I'm going to put it in scientific notation, times 10 to the 4th atoms thick. That has 3 significant figures. All right. So those are the calculations. Potential sources of error. So experimental error is what we're being asked about. You plugging into equations incorrectly is not an experimental error. Okay. You not being able to read something correctly. Well, again, there is estimation in that last digit. So if you blankly just said counting significant figures, again, we want to hone in on the fact that, well, yeah, my density from the aluminum cube that I used, that was based on measured values. There's uncertainty in those measured values. That's kind of the whole purpose of this whole activity and the whole unit about measurements. So there's uncertainty to the hundredths place of my lengths that I use to calculate my volume, that I use to calculate my density. That is introducing error every time I use numbers that have uncertainty in them, which is true of any measured value. That's where the error is coming from. So again, not talking about calculation errors. Some people mention about the masses from the balance being wrong. There's nothing wrong with my balances. So there is estimation in the last digit. That's true. So again, that is causing some estimating significant figure issues and accuracy issues later on down the line. But the number on the balance is the number on the balance. It's pretty not open to interpretation, so there's no reason for that to be an incorrect value, so you shouldn't be referencing that either, as long as you can read the numbers off of the scale. Lastly, for the percent error, the radius that you should have taken was 125 picometers. Again, the equation is the experimental value. So this is the one from my experiment. So that's my experimental value minus the accepted value divided by accepted times 100. Technically, when I subtract these two numbers, I get a 30 divided by 125. So I'm down to two significant figures times 100. And so that is going to give me 24%. So it's not the greatest, but it's not the worst. And again, we know that, or at least on the same order of magnitude, which if you were watching your units and careful, and again, most of us went wrong with algebra and units, we're at least in the same order of magnitude for our experimental value.